Hello, and welcome to a place of peace, wonder, and gentle discovery. In the next few hours, you're invited to slow down, to breathe deeply, and to let the rushing world fade into the background. This is a journey through a lazy meadow picnic, a space where time moves differently, where the simple act of observing becomes a doorway to extraordinary revelations. You don't need to do anything except be present. Let yourself settle in, get comfortable, and allow your mind to drift into the soft rhythm of meadow life. We'll be exploring 100 remarkable facts about wildflowers, clouds, and butterfly habits, but these won't be delivered as a list. Instead, they'll unfold naturally, woven together like the stems and petals of the meadow itself, each fact flowing into the next like water finding its path downhill. Here, you'll discover that buttercups use mirrors to warm visiting bees, that clouds can weigh 1,000,000 pounds yet float effortlessly, that butterflies taste the world through their feet and navigate by sensing magnetic fields invisible to us. You'll learn that what seems simple, a blade of grass, a passing cloud, a flutter of wings, is actually intricate beyond measure, the result of millions of years of adaptation and refinement. This is not a video that demands your full attention every moment. It's designed to wash over you like a gentle stream, sometimes in focus, sometimes in the peaceful background of your awareness. You might listen while resting, while relaxing before sleep, or during a quiet afternoon when you need to reconnect with something calm and true. So find your comfortable spot, perhaps in bed, in a favorite chair, or wherever you feel most at ease. Close your eyes if you wish, or let your gaze soften on something peaceful. Take a slow, deep breath, and let your shoulders drop away from your ears. The meadow is waiting for you. It's always been waiting, with its patient wisdom and quiet marvels, ready to share its secrets with anyone willing to listen. Let's begin our afternoon together. Picture yourself on a warm afternoon in late spring, when the world seems to slow down just enough for you to notice the small wonders around you. You've found the perfect spot, a sun-dappled meadow where the grass grows tall and soft, creating a natural carpet that seems to welcome you. As you spread your blanket across this green expanse, you're joining a tradition as old as leisure itself, settling into a space where wildflowers, clouds, and butterflies create an ever-changing tapestry of gentle beauty. The first thing you notice as you sit down is the incredible diversity of wildflowers surrounding you. What appears at first glance to be simply pretty flowers reveals itself to be a complex community. Wildflowers have evolved over millions of years to bloom at specific times, and each species follows its own internal calendar. The dandelions you see scattered throughout the meadow, those cheerful yellow faces that many consider weeds, are actually among nature's most efficient timekeepers. A single dandelion plant can produce up to 15,000 seeds in a season, each one attached to a delicate parachute designed to catch even the slightest breeze. As you lie back on your blanket, watching these seed heads drift past like tiny wishes floating through the air, you're witnessing a survival strategy perfected over countless generations. Each seed carries within it the complete blueprint for a new plant, waiting patiently for the moment it touches suitable soil to begin its transformation. Look closer at the flowers near your picnic spot, and you'll discover something remarkable about their colors. Those vibrant purples, yellows, and whites aren't just beautiful to human eyes, they're actually painted in colors we can't fully perceive. Many wildflowers reflect ultraviolet light, creating patterns and landing strips invisible to us but perfectly visible to bees and butterflies. The simple yellow buttercup beside your hand appears entirely different to a bee, marked with UV patterns that guide the insect directly to its nectar, like a tiny airport runway glowing in a spectrum beyond our vision. It's as if the flowers are speaking in a language we can only partially understand, their true messages hidden in light frequencies our eyes weren't designed to detect. Speaking of butterflies, you might notice a delicate monarch butterfly dancing from flower to flower near your blanket. These seemingly fragile creatures are actually incredible navigators undertaking one of nature's most impressive journeys. Monarch butterflies can travel up to 3,000 miles during their migration, navigating from Canada and the northern United States all the way to specific mountain forests in Mexico, forests that individual butterflies have never seen before, since they're several generations removed from the ancestors who made the previous journey. The butterfly you're watching may be preparing for this epic voyage, building up energy reserves with each sip of nectar. It uses an internal compass guided by the sun's position, the Earth's magnetic field, and an inherited memory passed down through its very genes, all contained within a brain smaller than a pinhead. As you settle deeper into your picnic blanket, tilt your head back and observe the clouds drifting overhead. Those seemingly solid white forms are actually massive collections of tiny water droplets or ice crystals, each cloud containing millions upon millions of these microscopic particles. A single cumulus cloud, one of those puffy, cotton-like clouds perfect for a lazy afternoon of cloud watching, can weigh over 1 million pounds. Yes, you read that right. That weightless-looking puff floating above you contains the equivalent weight of several hundred elephants, all suspended in the sky by gentle updrafts of warm air. And yet it floats, defying what seems possible, held aloft by invisible currents that cradle these massive water sculptures with effortless grace. The clouds above you are constantly shape-shifting, and there's actually a scientific reason why they form those particular shapes. Clouds form when warm, moist air rises and cools, causing water vapor to condense around tiny particles of dust, pollen, or even salt from ocean spray. Each cloud tells a story about the atmospheric conditions surrounding it, which is why meteorologists can predict weather by reading cloud formations like a book written across the sky. That towering cumulus cloud building on the horizon speaks of rising thermals and atmospheric instability, while the wispy cirrus clouds high above indicate winds at the edge of the troposphere, racing along at speeds that would take your breath away. Return your gaze to the meadow, and you might spot a small blue butterfly, perhaps a common blue or an azure, resting on a blade of grass. Butterflies are cold-blooded creatures, which means they cannot generate their own body heat like we do. This is why you often see them basking with their wings spread wide in patches of sunlight. A butterfly needs its body temperature to reach approximately 85 to 100 degrees Fahrenheit before it can fly effectively, which is why on cooler mornings, you'll find them sitting perfectly still on sun-warmed rocks and flowers, wings open like tiny solar panels, absorbing the warmth they need to begin their day. Watch one closely, and you might see it shivering, rapidly vibrating its wing muscles to generate just enough heat to prepare for flight, a patient ritual performed each morning before the day's adventures can begin. The wildflowers swaying gently around your picnic spot are engaged in one of nature's most beautiful partnerships. Many wildflowers have evolved alongside specific pollinators over thousands of years, developing relationships so precise that flower and pollinator are perfectly matched. The long, tubular flowers of wild columbine, for instance, have evolved their distinctive spurred shape specifically to accommodate the long tongues of hummingbirds and certain moths, while keeping out less effective pollinators. This means that each flower shape you see tells a story about which creatures visit it most frequently. The flat, open faces of daisies welcome a variety of visitors, while the deep throats of foxgloves reserve their treasures for bumblebees strong enough to push their way inside. As a gentle breeze passes over the meadow, notice how the clouds respond to the wind. While clouds appear to drift slowly and peacefully across the sky, the individual water droplets inside them are actually in constant, rapid motion. Inside a cloud, these droplets are continuously evaporating, condensing, colliding, and merging with one another at incredible speeds, even though the cloud itself seems to float serenely overhead. It's a reminder that stillness and activity can exist simultaneously, depending on your perspective, much like this peaceful meadow, where beneath the apparent calm, thousands of insects, plants, and microorganisms are engaged in the busy work of living. The same breeze that reshapes the clouds above also carries the sweet fragrance of wildflowers to your nose, molecules of scent traveling on invisible air currents, connecting you to blooms you haven't even noticed yet. And finally, as you take a deep breath of the flower-scented air and feel the sun warm on your face, consider this: the butterflies visiting the flowers around you taste with their feet. When a butterfly lands on a flower or leaf, special sensors on its feet can immediately detect whether the plant is suitable for feeding or egg-laying. It's one of nature's most elegant solutions. A butterfly can land and instantly know everything it needs to know about its landing spot, making decisions in microseconds that determine its survival. Imagine experiencing the world this way, where every step provides information, where landing and knowing are the same action. So here you are, in your meadow, surrounded by time-traveling monarchs, flowers painted in invisible colors, million-pound clouds, and butterflies that taste the world through their toes. The grass beneath your blanket continues its slow, patient growth. The flowers turn imperceptibly to follow the sun's arc. The clouds reshape themselves in an endless dance. And you, right here in this moment, are part of it all, a peaceful observer in nature's greatest ongoing performance. This is just the beginning of our journey through the quiet wonders of a lazy meadow picnic. As you sink further into the comfort of your meadow retreat, time seems to lose its urgency. The afternoon sun has shifted slightly, casting longer shadows across the wildflowers, and you begin to notice details you missed before. This is the gift of stillness. The longer you remain quiet, the more the meadow reveals its secrets. Reach out and gently touch one of the wildflowers beside your blanket. That simple stem you're holding is actually a marvel of engineering. Wildflower stems contain specialized tubes called xylem and phloem that work like a plant circulatory system, and they can move water from the roots to the flower at speeds of up to 100 feet per hour, defying gravity through a combination of capillary action and evaporation. The water you see glistening on the petals didn't just passively seep upward, it was actively pulled through microscopic channels, molecule by molecule, in an unbroken chain that stretches from the deepest roots to the highest bloom. This process continues day and night, as long as the plant lives, a silent fountain constantly flowing upward. Look up again at those magnificent clouds drifting across the azure sky. You might notice that some clouds have flat bottoms, as if they've been sliced with a knife. This isn't random, it marks the exact altitude where rising air cools enough for water vapor to condense. This level is called the lifting condensation level, and it's like an invisible ceiling in the sky where the transformation from invisible vapor to visible cloud occurs. Every flat-bottomed cloud you see is painting a line across the sky that marks a specific temperature and pressure boundary, turning the atmosphere into a readable map for those who know how to interpret it. A flutter of wings catches your attention, and you watch as a swallowtail butterfly lands on a purple thistle nearby. Here's something extraordinary: butterflies can see a wider range of colors than humans can. While we have 3 types of color receptors in our eyes, many butterflies have 5 or even 6, allowing them to perceive colors in the ultraviolet and far-red spectrum that are completely invisible to us. When that swallowtail looks at the meadow, it sees a world far more colorful and complex than the one we perceive, a hidden dimension of color that exists all around us, forever beyond our direct experience. The meadow you're enjoying is just one version of countless meadows, each perceived differently by every creature that visits. Notice the white clover scattered throughout the grass near your picnic blanket. These humble plants are performing an invisible miracle beneath the soil. Clover roots form partnerships with special bacteria that can capture nitrogen directly from the air and convert it into a form plants can use, a process called nitrogen fixation. In fact, a healthy clover plant can fix up to 200 pounds of nitrogen per acre per year, essentially pulling one of life's most essential nutrients out of thin air and making it available to every plant in the meadow. The clover beneath your blanket is literally feeding its neighbors, enriching the soil for the grasses and wildflowers that surround it, a quiet act of generosity happening in the darkness below ground. As the breeze picks up slightly, watch how the clouds respond to these invisible rivers of air. Clouds don't just float randomly, they follow wind currents at different altitudes, and these currents often move in completely different directions. The low clouds you see might be drifting east while higher clouds race westward, revealing the layered nature of our atmosphere. Meteorologists call these different layers the planetary boundary layer, the free atmosphere, and the upper atmosphere, each with its own weather patterns, wind speeds, and characteristics. You're watching a three-dimensional dance, where clouds at different heights tell different stories about the complex ocean of air surrounding our planet. A small copper-colored butterfly lands briefly on your hand, and you marvel at how delicate it seems. But here's a surprising fact: despite their fragile appearance, butterfly wings are remarkably strong and flexible. The wings are covered with thousands of tiny scales, which is why butterflies belong to the order Lepidoptera, meaning scale wing, and these scales overlap like roof shingles, providing both color and structural support. A butterfly can lose up to 20 to 30% of its wing scales and still fly effectively. Those scales you sometimes see as powder on your fingers after touching a butterfly's wing aren't essential for flight, they're more like decorative armor, beautiful and functional, but not individually critical to the butterfly's survival. Turn your attention to the various wildflowers creating patches of color throughout the meadow. Different flowers bloom at different times of day, and this isn't coincidental. Many wildflowers have evolved to open and close their petals in rhythm with their most effective pollinators' schedules. Morning glories open at dawn to greet early rising bees, while evening primrose blooms save their display for dusk, when moths emerge. Some flowers, like the purple oxalis you might spot near your blanket, are so punctual in their opening and closing times that Swedish botanist Carl Linnaeus once designed a flower clock garden, where he could tell the time of day by observing which flowers were open. The meadow itself is keeping time, each flower a hand on nature's clock. Above you, a particularly large cumulus cloud has developed what looks like a towering pillar rising from its center. This formation, called cumulus congestus, reveals that strong updrafts are building within the cloud, potentially developing into an afternoon thunderstorm. Inside that cloud, water droplets are being carried upward at speeds that can exceed 60 miles per hour, rising thousands of feet, freezing into ice crystals, and falling back down, only to be caught by updrafts and carried aloft again. This cycle can repeat dozens of times, with each journey adding layers of ice to what will eventually become a raindrop or even a hailstone. That peaceful-looking cloud is actually a vertical wind tunnel of incredible power, where water undergoes transformation after transformation in its journey from vapor to rain. A monarch butterfly drifts past, and you remember the one you saw earlier. Here's something that might surprise you: monarch butterflies that emerge in late summer are fundamentally different from those born in spring and early summer. The autumn generation, called the super generation, can live up to 8 months, nearly 10 times longer than their spring and summer relatives, which survive only 2 to 6 weeks. These supergeneration monarchs are the ones that make the epic migration to Mexico, and their bodies undergo remarkable changes to prepare for the journey. They store extra fat, their reproductive systems remain immature to conserve energy, and their wing muscles develop differently to sustain the long flight. The butterfly you're watching might be one of these remarkable individuals, already transformed for an odyssey that will span a continent. The afternoon light has grown warmer, more golden, and the shadows have lengthened across your meadow sanctuary. The wildflowers seem to glow in this light, the clouds have taken on subtle hints of amber, and butterflies continue their eternal dance from bloom to bloom. You've been here for a while now, and yet it feels like you've only just arrived. In this meadow, you're learning to read a language written in petals and wing scales, in water vapor and wind. Every element tells a story, and every story connects to countless others, weaving together in patterns both ancient and immediate. The meadow asks nothing of you except your presence, and in return, it offers wonders without end. The afternoon deepens around you, and you find yourself noticing the smaller worlds within this meadow, the intricate ecosystems that exist at every scale. A ladybug climbs a grass stem near your outstretched hand, and you realize that from its perspective, this meadow is as vast and unexplored as an ocean might be to you. Everything is relative here, and every creature experiences this space in its own unique way. Your eyes are drawn to a patch of wild daisies swaying rhythmically in the breeze. These cheerful flowers, with their white petals radiating from sunny yellow centers, hold a secret in their structure. What appears to be a single daisy flower is actually a composite of dozens or even hundreds of tiny individual flowers working together. The white petals you see are each separate ray flowers, while the yellow center is composed of numerous disc flowers, each one a complete flower in miniature with its own reproductive parts. A single daisy head might contain 50 to 80 individual flowers, all collaborating to create what we perceive as one bloom. It's a community masquerading as an individual, a collective that achieves together what none could accomplish alone. Above you, the clouds continue their leisurely procession across the sky, and you notice something curious. Some clouds seem to be evaporating before your eyes, their edges growing wispy and transparent. This process, called cloud dissipation, happens when a cloud drifts into drier air or descends into warmer temperatures. The water droplets that make up the cloud begin to evaporate faster than new ones can form, and the cloud gradually fades away like a watercolor painting left in the rain. What's remarkable is that the water doesn't disappear, it simply returns to its invisible vapor state, waiting in the air for the right conditions to condense once again into visible form. Clouds are constantly being born and dying all around you, temporary sculptures in an ever-changing gallery. A small painted lady butterfly lands on a black-eyed Susan near your picnic spot, and you're struck by the intricate patterns on its wings. But those beautiful markings serve a purpose beyond aesthetics. Many butterflies have evolved eye spots, circular patterns that resemble eyes, on their wings as a defense mechanism against predators. When a bird or lizard attacks, it often strikes at what it perceives to be the butterfly's head, these false eye spots near the wing edges. This allows the butterfly to escape with only minor wing damage rather than a fatal injury to its actual head and body. Some butterflies even have small tail-like projections near these eye spots that wiggle in the breeze, mimicking antennae and further convincing predators that they're attacking the wrong end. It's an elaborate deception, painted in scales, that has saved countless butterfly lives over millions of years. You reach down and run your fingers through the meadow grass beside your blanket. This grass, seemingly so simple and uniform, is actually engaged in sophisticated communication. When grass is cut, damaged, or eaten by insects, it releases chemical compounds into the air, a scent you might recognize as the smell of fresh-cut grass. But this pleasant aroma is actually a distress signal. These volatile organic compounds serve multiple purposes. They warn neighboring plants of danger, allowing them to increase their production of defensive chemicals, and they attract predatory insects that feed on the herbivores attacking the grass. The peaceful meadow around you is alive with chemical conversations, plants calling for help and warning their neighbors through an invisible network of scent molecules drifting on the breeze. Look up once more at the sky, and you might notice thin, wispy clouds stretched across the upper atmosphere like brushstrokes of white paint. These are cirrus clouds, composed entirely of ice crystals rather than water droplets, forming at altitudes of 20,000 feet or higher where the air is incredibly cold. Here's something fascinating. These ice crystals can remain suspended in the sky for hours or even days, and as sunlight passes through them, it bends and refracts, sometimes creating spectacular optical phenomena like halos, sun dogs, and arcs of rainbow-like color around the sun. Those delicate wisps you're watching are actually millions of tiny prisms, each one splitting sunlight into its component colors, creating a subtle light show that most people never notice. The sky is performing magic tricks with ice and light, and you have a front row seat. A butterfly, perhaps a common buckeye with its distinctive eye spots, flutters past, and you begin to wonder about their flight patterns. Unlike birds, butterflies don't fly in straight lines. Their erratic, zigzagging flight pattern isn't clumsy navigation, it's a brilliant survival strategy. This unpredictable flight makes them extremely difficult targets for predators to catch. A bird attempting to snatch a butterfly mid-flight has to constantly adjust its trajectory, and often the butterfly's sudden directional changes allow it to escape. Additionally, many butterflies intersperse their zigzagging with brief moments of gliding, which conserves energy during long-distance travel. What looks like random wandering is actually a sophisticated combination of predator evasion and energy management, refined over millions of generations. Near your blanket, you notice wild violets blooming in the shade of taller plants. These delicate purple flowers demonstrate one of nature's most fascinating adaptations to ensure reproduction. Violets actually produce two completely different types of flowers. The showy purple flowers you're admiring are designed to attract pollinators, but later in the season, violets produce tiny, closed flowers called cleistogamous flowers that never open at all. These hidden flowers self-pollinate and produce seeds without ever attracting a single insect. It's a two-strategy approach. When conditions are good and pollinators are abundant, the violet invests in beautiful, open flowers that encourage genetic diversity through cross-pollination. When conditions are uncertain, it produces the closed flowers as a backup plan, ensuring reproduction even without pollinators. The violet is hedging its bets, playing both the risky and the safe strategy simultaneously. The clouds above have begun to take on subtle colors as the afternoon progresses, hints of gold and the faintest suggestion of pink along their edges. This happens because of the angle at which sunlight passes through the atmosphere. As the sun lowers toward the horizon, its light must travel through increasingly more atmosphere to reach your eyes, and the atmospheric particles scatter the shorter blue wavelengths while allowing the longer red and orange wavelengths to pass through. This is why clouds begin to warm in color as the day ages. But here's something many people don't realize. The colors you see in clouds can actually tell you about the size of the water droplets within them. Clouds with smaller droplets appear more white or silver, while clouds with larger droplets can take on more vivid colors during sunrise and sunset. You're not just watching clouds change color, you're seeing information about the microscopic structure of those clouds revealed through the language of light. A tiger swallowtail butterfly dances past your field of vision, its distinctive yellow and black striped wings catching the golden light. Here's a remarkable fact about butterfly navigation. Many species, including monarchs and painted ladies, can detect the Earth's magnetic field and use it as a compass during migration. Scientists believe butterflies have special magnetic sensing proteins in their antennae that allow them to perceive magnetic fields, giving them an internal compass that works even on cloudy days when the sun isn't visible. The butterfly you're watching possesses a sense you don't have. It can feel the invisible lines of magnetic force that wrap around the planet, reading them like a map that guides its journey across thousands of miles. It's navigating through dimensions of reality that remain forever closed to human perception. You shift slightly on your blanket, and the movement sends a small copper butterfly fluttering up from where it had been resting on the corner of your picnic cloth. The afternoon has grown richer, deeper, full of golden light and lengthening shadows. The meadow hums with life, not just the life you can see, but the life you're only beginning to understand. The chemical conversations of the grass, the composite architecture of the daisies, the magnetic sense of migrating butterflies, and the ever-changing sculpture garden of clouds above. Here in this meadow, you're not separate from nature, you're woven into it, part of the same intricate tapestry that connects flowers to butterflies, clouds to grass, light to color, and one moment to the next. The meadow doesn't distinguish between observer and observed. It simply is, and so are you, sharing this space and this time. The sun has traveled further across the sky, and the quality of light in your meadow has transformed into something almost honeyed, thick and golden as it filters through the afternoon air. You've been here long enough now that the wildlife has accepted your presence, and creatures that might have kept their distance earlier now go about their business as if you're just another feature of the landscape, a warm rock, perhaps, or a particularly still tree. A bumblebee drones past your ear, heavy with pollen, making its way toward a cluster of lavender wildflowers at the edge of your blanket. Bumblebees are extraordinary creatures, and here's something that defies what seems possible. A bumblebee's wings are relatively small compared to its body weight, and for decades, scientists were puzzled by how these rotund insects could fly at all. The answer lies in the remarkable way they move their wings, not up and down like most flying insects, but in a complex figure-8 pattern, beating up to 200 times per second. This creates tiny hurricanes of air above and below the wing, generating enough lift to keep their fuzzy bodies aloft. The bumblebee you're watching is performing an aerodynamic miracle with every journey from flower to flower, defying outdated physics calculations with every beat of its wings. Your gaze drifts upward to where a new formation of clouds has begun to develop. These clouds look different from the ones you've been watching. They're arranged in parallel rows or waves across the sky, like ripples on a pond frozen in mid-motion. These are called cloud streets or wave clouds, and they form when wind encounters an obstacle like a mountain or even a temperature boundary, creating a wave pattern in the atmosphere. The clouds form at the crest of each wave where air rises and cools, while the spaces between represent the troughs where air descends and evaporates the cloud droplets. You're looking at wind made visible, the atmosphere revealing its invisible currents through these remarkable formations that can stretch for dozens or even hundreds of miles across the sky. A small blue butterfly, perhaps an azure or a holly blue, lands delicately on a stem of Queen Anne's lace nearby. This gives you a chance to observe something remarkable about how butterflies drink. Unlike bees, which have relatively short tongues, butterflies possess a long, coiled proboscis that works like a living straw. When not in use, this proboscis is coiled up like a watch spring beneath the butterfly's head, but when the butterfly finds nectar, it uncoils this remarkable feeding tube, which can be longer than the butterfly's entire body. Some species of butterflies have a proboscis that measures 3 or 4 times their body length, allowing them to reach nectar in the deepest flowers. The butterfly you're watching is using a piece of equipment more sophisticated than any human-made straw, a precision instrument that can navigate the complex architecture of flowers with perfect accuracy. You pluck a piece of grass and examine it more closely. This simple blade contains one of nature's most important innovations. Grasses, unlike most other plants, grow from the base rather than the tip. This means that when a grass blade is cut, eaten, or broken, it continues growing from the bottom, constantly regenerating itself. This is why grass can survive repeated mowing, grazing by animals, and even the trampling of countless feet. The meadow you're sitting in could be grazed by deer, walked across by hikers, and still regenerate within days. Each blade of grass you're touching is essentially immortal at its base, continuously producing new growth while its tips are sacrificed to herbivores and weather. It's a strategy that has allowed grasses to dominate nearly 40% of Earth's land surface, making them one of the most successful plant families in history. Above you, a single cloud catches your attention. It's darker than the others, its base a soft gray rather than brilliant white. This color change tells a story about what's happening inside. Clouds appear white when sunlight bounces off the water droplets and scatters in all directions, but when a cloud becomes very thick or its water droplets grow larger and more numerous, less light can penetrate through it. The gray cloud you're observing contains more water, and its droplets are likely growing heavier, possibly preparing to fall as rain. The color of a cloud is actually a measurement tool. The darker it appears, the more water it holds, and the more likely it is to release that water back to Earth. That gray-bottomed cloud is telling you its story if you know how to listen, announcing its increasing burden of water through the language of shadow and light. A monarch butterfly pauses on a patch of milkweed at the meadow's edge, and this encounter reminds you of one of nature's most intricate relationships. Monarch caterpillars feed exclusively on milkweed plants, and this pickiness serves a crucial purpose. Milkweed contains toxic compounds called cardiac glycosides that are poisonous to most animals, but monarch caterpillars have evolved the ability to consume these toxins without harm. Even more remarkably, they store these toxins in their bodies, remaining poisonous even after they transform into butterflies. The bright orange and black coloring of the monarch serves as a warning to predators: I taste terrible, and I might make you sick. Birds that attempt to eat a monarch once quickly learn to avoid all orange and black butterflies in the future. The butterfly you're watching is wearing its toxicity like a bright warning label, a defense inherited from the plant it ate as a caterpillar weeks or months ago. You notice wild strawberry plants sprawling near your picnic blanket, their small white flowers dotting the green foliage. These flowers reveal something fascinating about plant reproduction and fruit development. Unlike most flowers, strawberry blossoms have dozens of separate pistils, the female reproductive parts, all clustered together in the flower's center. When the flower is pollinated, each of these tiny pistils develops into what we call a seed on the outside of the strawberry, while the flower's receptacle, the part that held all these pistils, swells and ripens into the sweet red fruit we eat. This means that what we call a strawberry isn't technically a berry at all, but rather a swollen flower base covered with the plant's actual fruits, those tiny seeds on the outside. Each seed represents a separate fertilization event, which is why strawberries that are incompletely pollinated develop with one-sided or misshapen fruit. The flower you're looking at is preparing to turn itself inside out, transforming its architecture into something deliciously edible. The sky above has become a complex layering of different cloud types, each at its own altitude, each moving at its own speed. Here's something that might surprise you: clouds can actually create their own weather beneath them. When rain falls from a cloud, it evaporates as it passes through drier air below, and this evaporation cools the air, making it denser and heavier. This cooler air then sinks rapidly, creating downdrafts that can reach the ground as gusts of cool wind, sometimes arriving several minutes before any rain. This is why you often feel a sudden cool breeze and see tree branches tossing before a thunderstorm arrives. The clouds are sending advance messengers, currents of cooled air that announce the approaching rain like heralds before a king. A painted lady butterfly settles on your knee, apparently mistaking you for a particularly comfortable rock. This moment of trust allows you to observe the butterfly at close range, and you notice how its antennae are constantly moving, twitching, and rotating as it samples the air. Butterfly antennae are incredibly sophisticated sensory organs covered with thousands of tiny sensors that detect not just smells but also humidity, temperature, and even wind speed and direction. These antennae are so sensitive that a butterfly can detect the scent of flowers from over a mile away, or recognize the specific plant species its caterpillars need to eat, even among dozens of similar-looking plants. The butterfly resting on your knee is tasting the wind, reading the temperature, analyzing the humidity, and scanning for the chemical signatures of flowers and potential mates, all simultaneously, through those two delicate, club-tipped antennae that seem to dance in constant motion. The afternoon has reached that perfect point where time seems suspended between the active middle of the day and the approaching evening. The light has grown even more golden, the shadows longer and softer. The meadow wraps around you like a living blanket, and you realize you've stopped thinking about anywhere else you need to be. This is the gift of the meadow, not just beauty, though there is beauty everywhere. Not just peace, though peace settles over you like morning dew. The gift is connection, the recognition that you're part of something vast and intricate, where bumblebees defy physics, where clouds paint wind across the sky, where butterflies carry poison as protection, and where every blade of grass is engaged in its own quiet immortality. The afternoon continues its slow, luxurious drift toward evening, and you find yourself in that perfect state of relaxed alertness where you're calm enough to be still but awake enough to truly see. The meadow has become familiar now, almost like an old friend whose presence requires no effort, no pretense. You notice things you would have missed in your first moments here, the tiniest movements, the subtlest changes in light, the quiet dramas unfolding in miniature all around you. Your attention is drawn to a patch of red clover blooming near your outstretched hand. These cheerful pom-pom flowers are fascinating structures, and here's something remarkable: each of those round flower heads is actually composed of 50 to 100 individual tubular florets, and each tiny floret opens in sequence over several days. The florets at the base of the flower head open first, and the opening progresses upward like a slow wave moving through the bloom. This sequential opening means that a single clover head provides fresh nectar over an extended period, ensuring that pollinators return multiple times to the same flower head. It's a strategy that maximizes the chance of pollination while rationing the plant's resources efficiently. The clover you're looking at is actually dozens of flowers experiencing different stages of their life cycle simultaneously, a community progressing through time at different speeds within the same small space. Above you, the clouds have taken on new characteristics as the angle of sunlight changes. You notice some clouds have brilliant white, cauliflower-like tops that seem to glow against the deepening blue of the sky. These towering formations reveal powerful updrafts within the cloud, and here's something extraordinary: the moisture inside these rising columns of air is releasing heat as it condenses from vapor into liquid droplets. This process, called latent heat release, actually warms the air inside the cloud, making it even more buoyant and causing it to rise faster. In a sense, the cloud is fueling its own growth, using the energy stored in water vapor to power its vertical development. A large cumulus cloud can release as much energy as a small atomic bomb through this condensation process, though it does so gradually over hours rather than in a single instant. The peaceful clouds drifting overhead are actually tremendous engines of energy transformation, quietly demonstrating the immense power contained in something as simple as water changing state. A skipper butterfly, one of those small, moth-like butterflies with quick, darting flight, lands on a yellow hawkweed blossom nearby. Skippers get their name from their distinctive flight pattern, but here's what makes them truly unique: skippers are actually considered a bridge between butterflies and moths. They share characteristics with both groups, and scientists have debated their classification for years. Unlike most butterflies, skippers have relatively stout bodies and hook-shaped tips on their antennae. They also rest with their wings at unusual angles, often with hind wings flat and forewings raised, creating a distinctive jet plane silhouette. When the skipper on the hawkweed takes flight again, watch how it moves. Those rapid, buzzing wing beats and sudden directional changes are different from the leisurely floating of other butterflies. You're watching a creature that represents an evolutionary middle ground, a living reminder that nature doesn't always fit into the neat categories we create. You run your hand along the top of the grass, feeling the seed heads tickle your palm. These seeds represent one of humanity's most important relationships with the plant world. The ancestors of modern wheat, rice, corn, and oats were all wild grasses much like the ones growing in this meadow, and the cultivation of grass seeds, what we call grains, literally built human civilization. But here's something most people don't realize: grass seeds have evolved specifically to be eaten. Unlike many plants that produce toxins to discourage seed consumption, grasses have taken the opposite approach. They package their seeds in nutritious, edible coatings and produce them in enormous quantities, essentially bribing animals to eat them. The strategy works because while many seeds are digested, some pass through the animal's digestive system intact and are deposited far from the parent plant, complete with a package of fertilizer. The grass seeds brushing against your hand are employing a 10-million-year-old strategy: be so abundant and nutritious that even though most of you will be eaten, enough will survive to ensure the next generation. The clouds continue their slow transformation overhead, and you notice something curious. Some clouds seem to have distinct, sharp edges while others fade gradually into the surrounding sky. This difference tells you about the humidity of the air surrounding the cloud. When a cloud has crisp, well-defined edges, it means the surrounding air is quite dry, causing water droplets to evaporate quickly at the cloud's boundary. When a cloud has soft, fuzzy edges that blend into the sky, the surrounding air is more humid, allowing the cloud droplets to persist even as they diffuse outward. You're essentially seeing a humidity map written in cloud edges. Sharp boundaries mean dry air, soft boundaries mean moist air. The sky is constantly providing this information, drawing diagrams of atmospheric moisture for anyone who knows how to read them. A question mark butterfly, named for the distinctive silver marking on its underwing that resembles a question mark or perhaps a comma, lands on the fabric of your blanket. This gives you an opportunity to observe one of the butterfly's most remarkable features, its eyes. Butterflies have compound eyes, each eye made up of thousands of individual light-sensing units called ommatidia. A butterfly's eye might contain 6,000 to 17,000 of these units, each one capturing a tiny piece of the visual scene. The butterfly's brain then assembles all these fragments into a complete image, somewhat like a mosaic made of thousands of tiny tiles. But here's what's truly remarkable. This compound eye structure gives butterflies an almost 360-degree field of view. The butterfly on your blanket can see forward, backward, up, and down simultaneously, without moving its head. It lives in a world of constant, all-directional awareness, unable to be surprised by predators approaching from behind because behind is always visible. You exist in its field of vision even though it's not facing you, seen through hundreds of tiny lenses capturing your presence from multiple angles at once. Near your picnic spot, you notice thistles growing, those prickly purple flowers that seem more fortress than blossom. Thistles demonstrate a fascinating defensive strategy that goes beyond their obvious spines. The leaves of many thistle species are covered not just with thorns but also with a waxy coating that makes them difficult to chew and digest. But here's the clever part: thistle plants can actually adjust their defenses based on whether they're being eaten. When a thistle detects damage from herbivores, through chemical signals released by damaged plant tissue, it increases the production of both physical defenses like spines and chemical defenses like bitter compounds in its new growth. The thistle essentially learns from being attacked and adapts its defenses accordingly. The prickly plant you're looking at might be heavily armed because of past encounters with hungry insects or animals, its thorniness a memory of previous battles written in spines and toxins. You look up to see that some of the clouds have begun to develop what looks like a slightly greenish or yellowish tint at their bases. This color shift can indicate that a cloud contains a large amount of water or even ice, and in some cases, it might be a sign of developing severe weather. The greenish color occurs when sunlight passes through cloud layers containing both water droplets and ice crystals, along with possible hail. The specific wavelengths of light that make it through this complex mixture can give clouds an eerie green-yellow glow. Fortunately, the clouds above you show only the faintest hint of this color, suggesting moisture-laden clouds but nothing threatening. Still, it's a reminder that clouds are constantly communicating their internal states through color, shape, texture, and movement, a visual language that our ancestors learned to read for survival, and that we're only beginning to fully understand with modern instruments. A red admiral butterfly makes a territorial patrol past your blanket. These butterflies are known for defending favorite sunning spots and will chase away other butterflies, and even birds, that intrude on their territory. Here's something surprising about butterfly territoriality. The red admiral you're watching has a brain smaller than a pinhead, yet it can recognize individual landmarks, remember the boundaries of its territory, and distinguish between intruders that need to be chased away and potential mates that should be approached. Scientists have discovered that butterflies can form memories, learn from experience, and even make complex decisions based on past encounters. That tiny brain contains perhaps 1 million neurons, compared to the 86 billion in a human brain, yet it's enough to create what we might call personality, preference, and memory. The butterfly patrolling past you is not just an automaton following instinct, it's an individual with experiences, memories, and behaviors shaped by its unique life history. The sun has shifted noticeably now, and the shadows stretch long across the meadow. The temperature has dropped slightly, just enough to be noticeable, and the quality of light has become even richer, more saturated. Colors seem more vivid in this light, the purples more purple, the yellows more luminous, the greens deeper and more complex. You've been in this meadow long enough now that you're no longer a visitor, you've become part of its afternoon rhythm. The butterflies accept your presence, the bees work around you, and the clouds continue their eternal dance overhead without regard for your observation. You're woven into this moment, this place, this convergence of light and life and the slow turning of the earth beneath an ever-changing sky. The afternoon has reached that magical hour when everything seems to soften and glow. The sun hangs lower in the western sky, painting the meadow in warm amber tones, and there's a quality to the air now, something tangible, almost thick with golden light. You shift on your blanket, settling into a new position, and realize you've lost track of how long you've been here. Time has become irrelevant, measured only by the movement of shadows and the changing angle of sunlight. Your eyes fall upon a cluster of buttercups, their glossy yellow petals reflecting the afternoon sun like tiny mirrors. This reflective quality is no accident. Buttercup petals have a unique structure that makes them among the shiniest flowers in nature. The petals contain a special layer of cells filled with starch that act like a mirror, reflecting light back through the yellow pigment layer above. This creates an intense, almost metallic glow that makes buttercups visible to pollinators from remarkable distances. But here's the truly fascinating part. This reflective layer doesn't just make the flower more visible, it actually focuses light onto the center of the flower where the pollen and nectar are located, warming these areas by several degrees. Bees and other insects are attracted not just to the brightness of buttercups but also to their warmth. The flower you're looking at is essentially using light as a heating element, creating a cozy, warm landing pad for cold-blooded insects that need to maintain their body temperature. It's solar engineering at its finest, perfected over millions of years. Above you, the clouds have begun their transformation into evening mode. You notice mare's tail clouds, wispy, delicate streaks that look like brushstrokes across the upper atmosphere. These are fragments of cirrus clouds, and they're so high up that they exist in temperatures far below freezing, composed entirely of ice crystals rather than water droplets. Here's something remarkable: these ice crystals can remain suspended in the air for hours, slowly falling at speeds of about 1 foot per second, drifting laterally in high-altitude winds as they descend. A single ice crystal visible in the clouds above you might take 4 or 5 hours to fall from its formation altitude to the ground, if it makes it that far at all. Most will evaporate long before reaching the surface, sublimating directly from ice to vapor in the dry air below. The clouds you're watching are actually slow-motion ice falls, frozen waterfalls suspended in the sky, taking hours to accomplish what would take seconds on Earth's surface. A great spangled fritillary butterfly lands on a wild bergamot flower near your blanket, its orange wings decorated with an intricate pattern of black spots and silver spangles on the underwing. This butterfly's life cycle reveals one of nature's most patient strategies. Adult fritillaries lay their eggs near violet plants in late summer, and when the tiny caterpillars hatch, they don't begin feeding immediately. Instead, these newborn caterpillars, no bigger than a grain of rice, immediately seek shelter and enter a state of dormancy called diapause, essentially hibernating through the entire winter without eating a single meal. Only when spring arrives do these caterpillars finally emerge and begin feeding on violet leaves. The butterfly you're watching survived its first winter as a tiny, unfed caterpillar, waiting months in suspended animation before beginning its life in earnest. It's an extraordinary gamble, to be born, then immediately sleep through the harshest season, trusting that spring will come and food will be available. You pluck a dandelion seed head, one of those perfect white spheres of seeds ready to disperse. As you blow gently, the seeds spiral away on their downy parachutes, and you're witnessing one of nature's most sophisticated flight designs. Scientists have recently discovered that dandelion seeds don't fly like traditional parachutes. Instead, each seed creates a tiny, stable bubble of air called a separated vortex ring that forms above the parachute structure. This vortex ring is what keeps the seed aloft, not the parachute itself. What's remarkable is that this vortex is extremely stable and forms with minimal material. The dandelion parachute is 90% empty space, making it one of the most material-efficient flying structures in nature. Engineers are now studying dandelion seeds to develop better designs for small, passive flying devices. The seeds floating away from your hand are using an aerodynamic principle that humans only recently discovered, a flight method that seems to violate conventional understanding of how parachutes should work. The clouds above continue to evolve, and you notice a phenomenon you've seen before but never really thought about: cloud shadows racing across the landscape. When a cloud passes between the sun and earth, it creates a moving shadow that can travel across the ground at remarkable speeds. Depending on the cloud's altitude and the wind speed at that altitude, cloud shadows can move at 30, 50, or even 100 miles per hour across the landscape. You're watching darkness itself racing across the meadow, a wave of shadow that exists only because of the interaction between solid matter, the water droplets in the cloud, electromagnetic radiation, sunlight, and your position as an observer. The shadow passing over you is as ephemeral as anything can be. It's not a thing but rather the absence of a thing, darkness defined only by the light around it, a moving void created by floating water. A common buckeye butterfly perches on a blade of grass near your knee, and you can clearly see the large eye spots that give this species its name. These eye spots serve multiple purposes, but here's something particularly clever. When a buckeye is resting, it holds its wings closed, concealing the bright eye spots on the upper wing surface and displaying only the cryptically colored underwing. If a predator approaches, the buckeye suddenly snaps its wings open, revealing the large, startling eye spots in a flash of color and pattern. This sudden appearance of eyes can startle a predator just long enough for the butterfly to escape, a defense strategy called dymatic display or startle coloring. The butterfly near you is essentially carrying a hidden alarm system, a surprise defense that works specifically because it's concealed until the critical moment. It's wearing camouflage that can instantly transform into a warning, two opposing strategies housed in the same small body. You notice wild bergamot, also called bee balm, growing in a purple cluster nearby. The scent of these flowers carries on the breeze, and there's good reason for their fragrance. Bergamot flowers produce aromatic oils that contain compounds called monoterpenes, which give them their distinctive scent. But here's what makes this particularly interesting. These same compounds that attract pollinators also serve as natural antibiotics and antifungals, protecting the flower from disease. The plant has evolved a single solution to multiple problems: the oils that perfume the air, attracting bees and butterflies, also create a chemical shield against microbial infection. Indigenous peoples and early settlers recognized these medicinal properties and used bee balm to treat infections, fevers, and digestive problems. The fragrant purple flowers swaying near your blanket are simultaneously advertising to pollinators and defending themselves from invisible threats, their perfumes serving double duty in the constant work of survival. Looking up, you notice that the clouds have developed what meteorologists call mammatus formations, pouch-like structures hanging from the cloud base that look almost like upside-down bubbles or pouches. These formations appear when air inside the cloud is cooler and denser than the air below it, causing it to sink in pockets while the surrounding air rises. The result is these distinctive, sometimes dramatic bulges that can cover the sky in a pattern that looks almost like a bubble wrap or a field of clouds viewed from below. Mammatus clouds are often associated with severe thunderstorms, though their presence doesn't necessarily indicate danger. They simply reveal the complex vertical air movements happening within the storm system. The pouches hanging above you are actually parcels of cold air sinking into warmer air, each one a small descending current in the vast circulation system of the atmosphere, making visible the otherwise invisible churning of the air ocean in which we live. A morning cloak butterfly, one of the longest-lived butterfly species in North America, glides past on dark, velvety wings edged with a band of cream yellow. Here's something extraordinary about morning cloaks. While most butterflies live only a few weeks as adults, morning cloaks can survive for 10 to 11 months. They accomplish this remarkable longevity through a survival strategy that seems almost supernatural. These butterflies actually hibernate through the winter as adults. In autumn, they seek out protected spots under bark, in wood piles, or in other sheltered locations, and enter a state of dormancy. Their bodies produce a natural antifreeze, a compound called glycerol, that prevents ice crystals from forming in their cells and killing them. When spring arrives, these butterflies emerge from hibernation and are often among the first butterflies seen each year, sometimes flying when snow still covers the ground. The morning cloak drifting past you might be months old, a survivor of winter, carrying within its body the chemical knowledge of how to transform water into something that won't freeze, a tiny miracle of biochemistry wrapped in wings. The light has grown even more golden, and the meadow seems to breathe around you, the grass moving in waves, the flowers nodding on their stems, butterflies tracing invisible patterns through the air. Everything is connected here, every element part of a greater whole, and you're inside that whole, not separate from it but woven into its fabric as surely as the threads in your picnic blanket are woven together. The meadow asks nothing from you except presence, and in return, it offers endless wonders. Flowers that heat themselves with reflected light, seeds that fly on invisible vortexes, butterflies that survive winter by transforming their blood chemistry, and clouds that reveal the hidden architecture of wind and temperature. You're surrounded by miracles performing themselves without audience or applause, simply because this is what life does: it adapts, persists, and creates beauty as a byproduct of survival. The afternoon is giving way to early evening now, though the transition is so gradual you can barely perceive it happening. The light has taken on that quality photographers call the golden hour, where everything glows as if lit from within. The meadow has become a study in amber and honey-colored light, each blade of grass edged in gold, each flower petal luminous. You've been still for so long that you've almost forgotten the world beyond this place, and the meadow has rewarded your patience by revealing deeper layers of its existence. Near your hand, a spiderweb stretches between two tall stalks of grass, and the evening light catches it perfectly, transforming it into strings of light studded with dewdrops. Spider silk is one of nature's most remarkable materials, and the web you're looking at represents an engineering feat that humans still struggle to replicate. Spider silk, weight for weight, is stronger than steel and more elastic than rubber. A strand of spider silk the thickness of a pencil could theoretically stop a Boeing 747 in flight. But here's what makes it truly extraordinary: spiders produce this supermaterial at room temperature, using only the proteins from the insects they eat as raw material, and they can produce several different types of silk from different glands, each optimized for specific purposes, some for web structure, some for wrapping prey, some for creating egg sacs. The delicate web before you, glistening with moisture, is actually a high-tech composite structure built by a creature with a brain smaller than a pinhead, using manufacturing processes that represent some of the most sophisticated materials science in the natural world. Above you, the clouds have begun to show the first hints of pink and orange along their edges, painting the approaching evening. As the sun lowers toward the horizon, its light must travel through increasingly more atmosphere to reach your eyes, and this long journey through air filters out different wavelengths of light. But here's something most people don't know: the colors you see in evening clouds aren't actually in the clouds themselves, they're reflections of colors in the sky around and behind the clouds. Clouds have no color of their own, they simply reflect whatever light reaches them. When a cloud appears pink or orange during sunset, it's reflecting the warm colors from the sky, acting like a three-dimensional screen displaying the sunset from multiple angles. The clouds are essentially mirrors, curved and sculpted, showing you the sunset not just where the sun touches the horizon but scattered across the entire dome of the sky. A pearl crescent butterfly, small and delicate, lands on a black-eyed Susan near your blanket. These butterflies are among the most common in North America, but their abundance doesn't diminish their remarkable nature. Pearl crescents have an unusual life strategy. They can produce multiple generations in a single year, sometimes as many as 3 or 4. Each generation from egg to adult butterfly takes only about a month, allowing them to exploit the brief abundance of their host plants, various species of asters, throughout the growing season. But here's the fascinating adaptation. The final generation of pearl crescents born in late summer is fundamentally different from its parents. These autumn individuals don't reproduce immediately. Instead, they enter hibernation as partially grown caterpillars, waiting out the winter in rolled leaves or other protected spots. The butterfly you're watching might be a grandchild or great-grandchild of the butterflies that emerged in spring, part of a rapid-fire succession of generations rushing to reproduce before winter arrives. You notice a patch of bird's foot trefoil growing near the edge of your blanket, its cheerful yellow flowers tinged with red. These flowers demonstrate one of nature's most economical design principles. Bird's foot trefoil flowers change color as they age. They start as bright yellow when freshly opened and full of nectar, then gradually shift to orange and finally to red as the nectar is depleted and the flower is pollinated. This color change serves as a signal to pollinators, essentially telling them, "Don't waste your time here, this flower is already pollinated and empty of nectar. Visit the yellow ones instead." This benefits both the plant and the pollinator. Bees don't waste energy visiting flowers that have nothing to offer, and the plant directs pollinators toward flowers that still need pollination. It's a communication system based on color change, a visual language that has evolved to maximize efficiency for both parties in this ancient partnership. The clouds continue their slow evening transformation, and you notice something peculiar. Some clouds seem to be moving in completely different directions at different altitudes. This isn't an optical illusion, it's revealing the layered structure of the atmosphere. At different heights, winds can blow in completely different directions and at vastly different speeds. Meteorologists call this wind shear, and it's one of the most important factors in weather formation. The clouds at 5,000 feet might be moving east while clouds at 20,000 feet race westward, and clouds at 35,000 feet might barely move at all or flow in yet another direction. You're watching a three-dimensional river system, where currents at different depths flow in different directions, all invisible except where clouds make them apparent. The sky above you is a stack of rivers, each flowing independently, each carrying its cargo of moisture and energy in different directions across the continent. A common wood nymph butterfly, dressed in brown and gray with distinctive eye spots, flutters up from the grass where it had been nearly invisible. This butterfly's coloring demonstrates what biologists call crypsis, camouflage designed to make an organism blend with its surroundings. But here's what makes the wood nymph strategy particularly clever. When it lands, it always does so with wings closed, and it consistently orients itself to align with grass stems and shadows. This isn't random. The butterfly has an instinctive understanding of how to position itself to maximize camouflage. Additionally, wood nymphs often land on bark or in dappled shade, environments where their brown, mottled coloring provides the best concealment. The butterfly chooses its landing spots based on where its coloration will work best. It's not just wearing camouflage, it's actively selecting backgrounds that make the camouflage effective, demonstrating a sophisticated understanding of how its appearance relates to its environment. Near your picnic spot, you notice yarrow growing, its flat-topped clusters of tiny white flowers creating landing platforms for small insects. Yarrow has been used medicinally for thousands of years. Its scientific name, Achillea, comes from the Greek hero Achilles, who supposedly used it to treat his soldiers' wounds. But here's the remarkable botanical fact: a single yarrow plant can produce up to 25,000 seeds, and these seeds can remain viable in the soil for up to 9 years, waiting for the right conditions to germinate. This means that the yarrow you're looking at might have siblings still sleeping in the soil, seeds that fell years ago and haven't germinated yet, waiting patiently for their moment. The plant is essentially spreading its reproduction across time, hedging against bad years by creating a seed bank that can wait out unfavorable conditions. Some of those seeds may never germinate, but others might spring to life years from now, long after the parent plant has died, carrying the same genetic information forward through time like messages in bottles buried in the earth. Looking upward, you see that the clouds have developed what looks like rays of light streaming through gaps between them, those dramatic shafts of illumination that seem almost supernatural. These are called crepuscular rays, and they're actually parallel shafts of sunlight that only appear to radiate outward because of perspective, the same effect that makes railroad tracks appear to converge in the distance even though they remain parallel. What you're seeing is sunlight streaming through gaps in the clouds, with the shadowed areas between beams appearing dark by contrast. The rays seem to spread outward from the sun like the spokes of a wheel, but this is an optical illusion created by your position as an observer. Those parallel beams of light are traveling 93 million miles from the sun to illuminate the meadow around you, and the clouds are simply creating windows and walls in this cosmic flood of light, making visible what is usually invisible, the actual paths that sunlight takes through the atmosphere. A Baltimore checkerspot butterfly, uncommon and beautiful with its intricate pattern of orange, white, and black, lands briefly on a turtlehead flower at the meadow's edge. This butterfly demonstrates one of nature's most specific dependencies. Baltimore checkerspot caterpillars eat almost exclusively turtlehead plants and a few related species, and they won't accept substitute food even if they're starving. This extreme specialization means that Baltimore checkerspots can only live where their specific host plants grow, making them excellent indicator species for habitat health. But here's the remarkable part: this extreme pickiness is actually a survival strategy. By specializing so completely, the caterpillars have evolved to efficiently process plants that are toxic to other insects. They face less competition for food because few other species can eat what they eat. The butterfly you're watching exists because its ancestors chose to specialize rather than generalize, betting everything on the continued existence of one particular plant species, a risky strategy that has nevertheless succeeded for millions of years. The light continues to deepen and warm, and the meadow seems to be preparing for evening, though true darkness is still hours away. The air has cooled just slightly, carrying with it the mixed fragrance of grass and wildflowers, a scent that's somehow both green and sweet. The shadows have grown long enough that they're merging into larger pools of shade, and the illuminated areas glow even more brilliantly by contrast. You realize that you've witnessed an entire afternoon pass in this meadow, and yet it feels like you've only scratched the surface of what's here. Every square foot of this space contains entire universes of interaction and adaptation, stories written in silk and pollen, in color-changing flowers and camouflaged butterflies, in clouds that mirror the sky and seeds that wait years for their moment. The meadow is a library of living knowledge, and you're only beginning to learn its language. The golden hour has reached its peak, and the meadow is bathed in light so rich and warm it seems almost tangible, as if you could reach out and touch the luminous air itself. Everything has taken on a dreamlike quality, edges soften, colors deepen, and the boundary between the day that was and the evening that's approaching blurs into this perfect, suspended moment. You've become so still, so integrated into this space, that a small rabbit has ventured close to your blanket, pausing to nibble clover blossoms, apparently unconcerned by your presence. Your gaze settles on a patch of purple vetch winding through the grass, its tendrils reaching and climbing wherever they can find support. Vetch is a member of the legume family, and like its cousins the clovers and peas, it has a remarkable ability. The roots of vetch plants form nodules, small, round swellings where bacteria called rhizobia live in a mutually beneficial partnership. These bacteria have the extraordinary ability to convert atmospheric nitrogen into ammonia, a form of nitrogen that plants can absorb and use. In exchange for this service, the plant provides the bacteria with sugars and a protected environment. But here's the truly remarkable part: this nitrogen-fixing process requires an enormous amount of energy. Fixing a single nitrogen molecule requires breaking a triple bond, one of the strongest bonds in chemistry, and this takes as much energy as the bacteria would normally use for all their other life processes combined. The delicate purple flowers you're looking at are supported by an underground partnership that performs one of nature's most energy-intensive chemical reactions, turning thin air into fertilizer through sheer biological determination. Above you, the clouds have begun to show more dramatic colors, deeper oranges, soft pinks, and even hints of purple along their undersides. As the sun continues its descent, the light must pass through an increasingly thick layer of atmosphere, and this extended journey through air molecules causes something called Rayleigh scattering. The shorter blue and green wavelengths of light are scattered away in all directions, while the longer red and orange wavelengths continue straight through to your eyes and to the clouds above. But here's something fascinating: the intensity of sunset colors is actually enhanced by tiny particles in the atmosphere. Dust, pollen, pollution, and even volcanic ash can make sunsets more spectacular. After major volcanic eruptions, sunsets around the world become more vivid for months or even years as stratospheric ash particles scatter light in particularly dramatic ways. The colors painting the clouds above you are the result of sunlight's long journey through miles of air, filtered and sorted by molecules and particles, with each wavelength taking a different path, creating a natural light show that's never quite the same twice. A cloudless sulfur butterfly, bright yellow and energetic, dances past your blanket in the characteristic fast, erratic flight pattern of sulfur species. These butterflies are strong flyers and long-distance migrants, but here's what makes them particularly interesting. Male cloudless sulfurs are bright yellow, but females can be either yellow or white. This color variation in females is called polymorphism, and scientists believe it serves multiple purposes. The white form may be less visible to predators, while the yellow form may be more attractive to males. Some research suggests that the white form also absorbs less heat, which could be advantageous in hot weather. The butterfly you're watching exists in a species where females have essentially two different survival strategies encoded in their genetics, and which strategy an individual female employs is determined by her genes. It's evolution keeping multiple options open, maintaining genetic diversity by allowing different approaches to the same challenges of survival and reproduction. You notice ox-eye daisies nodding in the breeze, their white petals surrounding yellow centers in the classic daisy form that seems almost archetypal. But here's something you might not know: daisies exhibit a behavior called nyctinasty. They close their petals at night and reopen them in the morning. This isn't a response to light directly, but rather to temperature changes and the plant's internal circadian rhythm. The daisy has an internal biological clock that tells it when to open and close, and this schedule can continue even if the plant is kept in constant darkness or constant light. The mechanism involves differential growth rates on the upper and lower sides of the petals, causing them to curl closed or open flat. The daisies you're watching will close tonight, protecting their reproductive organs from cold and moisture, and will open again tomorrow morning to greet the sun, following a rhythm as reliable as the tides, driven by an internal timekeeper that evolved over millions of years to match the planet's rotation. The clouds above have developed into a spectacular display now, with layers at different altitudes showing different colors, the highest clouds still catching direct sunlight and glowing nearly white, the middle layers showing soft pinks and oranges, and the lowest clouds taking on deeper purples and grays. This vertical stratification of color reveals the spherical geometry of Earth and the Sun's position below the horizon from the perspective of different altitudes. The highest clouds can still see the sun even when it's set from your ground-level viewpoint. In fact, clouds at very high altitudes can remain sunlit for more than an hour after sunset as seen from the ground. You're watching a demonstration of Earth's curvature, written in light and cloud, showing how the planet's roundness creates different sunset times for different altitudes, all visible simultaneously in the layered colors of the evening sky. A pearl crescent butterfly makes one last visit to the bergamot flowers nearby, and you notice how it carefully probes each flower with its proboscis, searching for nectar. But butterflies aren't just mindlessly visiting flowers at random. They can actually learn and remember which individual flowers they've already visited and which ones are likely to still have nectar. Studies have shown that butterflies can remember the locations of rewarding flowers and will preferentially return to those spots. They can even learn to associate certain colors or patterns with the presence of nectar and adjust their foraging behavior accordingly. The butterfly you're watching has a mental map of this meadow, complete with annotations about which flowers are worth visiting and which should be skipped. That tiny brain, no larger than a grass seed, contains spatial memory, learned associations, and decision-making capabilities that guide every choice the butterfly makes as it forages through its territory. Near the base of your blanket, you spot self-heal growing, a low plant with purple flower spikes. Self-heal is another member of the mint family, and it demonstrates a fascinating adaptation to different growing conditions. When self-heal grows in frequently mowed areas or places where it's regularly grazed, it stays low to the ground, sometimes flowering at heights of less than an inch, keeping its precious flowers below the blade or teeth that might destroy them. But when the same plant grows in an undisturbed meadow, it can reach heights of 12 inches or more. This isn't different species or even different varieties, it's the same plant exhibiting phenotypic plasticity, the ability to develop differently based on environmental conditions. The self-heal you're looking at has essentially measured its environment and adjusted its growth pattern accordingly, demonstrating that while genes provide instructions, those instructions often include conditional statements: if frequently cut, grow low; if undisturbed, grow tall. It's a genetic program with built-in flexibility, allowing a single set of instructions to produce different outcomes in different circumstances. Looking up once more, you notice that some clouds have developed a silvery edge where sunlight strikes them at a particular angle, a phenomenon sometimes called a silver lining, though meteorologists call it cloud iridescence when it shows colors. This effect occurs when light waves diffract around the uniform water droplets at the edge of a cloud, causing interference patterns that can produce brilliant colors or silvery white edges. The effect is most visible when the cloud droplets are all approximately the same size, which happens in newly formed clouds where the droplets haven't had time to grow at different rates. The silvery edge you're observing is actually a diffraction pattern, the same physics that creates the colors in a soap bubble or an oil slick, but on a massive scale involving billions of water droplets all acting together to bend and interfere with light in coordinated ways. A red-spotted purple butterfly glides past on dark wings marked with iridescent blue and, despite its name, small red-orange spots near the body. This butterfly demonstrates one of nature's most remarkable examples of evolutionary mimicry. The red-spotted purple looks very similar to the pipevine swallowtail, a species that's toxic to birds because its caterpillars eat toxic pipevine plants. Birds learn to avoid pipevine swallowtails after attempting to eat one, and the red-spotted purple benefits from this learned avoidance even though it's completely harmless and edible. This is called Batesian mimicry, a harmless species evolving to look like a dangerous one. But here's what makes this particularly fascinating. In the southern part of its range where pipevine swallowtails are common, the red-spotted purple maintains this dark mimetic coloration. But in the northern part of its range where pipevine swallowtails are rare or absent, the same species exists in a different form, the white admiral, with white bands across its wings and completely different coloring. The same species uses different survival strategies in different regions based on which local butterflies are toxic. Evolution has written two different disguises into the same genetic code, and geography determines which one gets expressed. The evening continues to deepen around you, the light growing richer and more complex with each passing minute. The meadow has shifted from a place of bright afternoon energy to something more contemplative, more introspective. Shadows pool in every hollow, while the remaining sunlit areas glow with almost supernatural brilliance. The temperature has dropped noticeably now, and you can feel the first hints of evening coolness in the air. You've spent an entire afternoon in this meadow, and it has transformed you in ways you're only beginning to understand. You came here perhaps seeking rest or escape, but what you've found is connection to the intricate web of life that surrounds you, to the physics of light and water, to the deep time of evolution written in every flower and wing, to the present moment unfolding continuously around you. The meadow has taught you its language, or at least shown you that such a language exists, waiting to be learned by anyone willing to sit still long enough to listen. The sun is approaching the horizon now, its lower edge just touching the distant line where earth meets sky. The light has taken on that extraordinary quality that exists for only a brief window each day, neither quite day nor approaching night, but something in between, a liminal time when the world seems to hold its breath. The meadow around you has been transformed into a landscape of contrasts, deep shadows and brilliant highlights, warm amber light against cool blue shade. You feel the day releasing its hold, and evening beginning to claim the world. A small copper butterfly, russet orange with dark spots, lands on a seed head nearby, and you marvel at how these tiny creatures have found ways to thrive in every corner of this meadow. Small coppers demonstrate something remarkable about butterfly thermoregulation. On cool mornings or evenings like this one, you'll often see them basking with their wings held at specific angles to maximize sun exposure. But here's the fascinating detail: they don't just spread their wings flat, they actually angle them in a V shape, creating a natural solar collector that focuses warmth onto their body. The wings act like reflectors, bouncing additional sunlight onto the butterfly's thorax where the flight muscles are located. Some butterflies can raise their body temperature by as much as 20 degrees Fahrenheit above the ambient air temperature using this technique. The butterfly you're watching is essentially using its wings as solar panels and reflectors combined, actively managing its body temperature through geometry and positioning, a conscious use of physics that allows it to remain active even as the evening cools. Above you, the clouds have become a masterpiece of color, layers of rose, coral, deep orange, and purple stacked across the sky like a painting in progress. As the sun drops lower, the light must travel through even more atmosphere, and the colors intensify. But here's something remarkable about the timing of sunset colors: the most dramatic colors often appear not when the sun is setting, but about 10 to 20 minutes after it has dropped below the horizon. This is when the sun is at the perfect angle to illuminate the undersides of high clouds while you stand in shadow on the ground below. Photographers call this the afterglow, and it can sometimes be even more spectacular than the sunset itself. The display you're watching will continue to evolve and intensify for another 15 minutes or more after the sun disappears, painting the sky with colors that seem almost impossible, as if the atmosphere itself is glowing. You notice a small spider building a web between two flower stalks, and it reminds you of the web you observed earlier. Spiders don't build their webs randomly, they follow sophisticated algorithms that have been refined over hundreds of millions of years. An orb weaver spider, for instance, first establishes the outer frame of the web, then creates the radial spokes, and finally spirals inward laying the sticky capture thread. But here's what's truly remarkable: spiders build different types of webs depending on the weather conditions. On windy days, they build stronger, more resilient webs with thicker threads and more anchoring points. On humid nights when flying insects are most active, they build larger webs with more sticky spiral threads to maximize capture area. The spider you're watching isn't just following blind instinct, it's making real-time engineering decisions based on environmental conditions, adjusting its construction techniques to optimize for current weather and prey availability. Each web is a custom solution to the specific challenges of that day, that location, that weather pattern. Near your blanket, you spot wild strawberry plants with small white flowers that have now closed for the evening. Many flowers exhibit this closing behavior as light fades, and it's driven by multiple factors. Temperature changes, light levels, and humidity all trigger responses in the flower petals, causing them to close. But here's the interesting part. This closing protects the flower's reproductive organs not just from cold and moisture, but also from nighttime visitors that might consume pollen without providing pollination services. By closing at night, flowers essentially restrict access to visitors who work during daylight hours, primarily bees and butterflies, and exclude nighttime visitors like certain beetles that might eat pollen without transferring it between flowers. The closed flowers around you are practicing selective access control, using time of day as a filter to ensure they only pay nectar rewards to the pollinators who actually provide the service they need. The sky continues its chromatic performance, and you notice something interesting. The clouds directly overhead have taken on a grayish-purple hue while clouds near the horizon glow with brilliant orange and pink. This color difference is due to your viewing angle and the amount of atmosphere the light must pass through. Light from clouds near the horizon has traveled through much more atmosphere to reach your eyes, undergoing more scattering and filtering. The warm colors you see there are the light that survived this long journey. Clouds overhead receive light that has traveled through less atmosphere, and they appear in cooler tones. You're essentially seeing multiple versions of sunset simultaneously, the overhead clouds showing you what sunset looks like from a shorter light path, while the horizon clouds display the most extreme filtering effects. The sky is demonstrating the physics of light scattering in 3 dimensions, with distance and angle creating this gradient of color from cool to warm, from purple to orange. A late foraging bumblebee works its way through the remaining open flowers, and you can hear the distinctive buzzing sound it makes. This buzz isn't just the sound of flying. Bumblebees use a technique called buzz pollination or sonication. They grab onto a flower and vibrate their flight muscles at specific frequencies without moving their wings, creating vibrations that shake pollen loose from flowers that wouldn't release it otherwise. Some plants, including tomatoes, blueberries, and cranberries, have evolved to release their pollen only in response to these specific vibrations. Honeybees can't perform buzz pollination. It's a specialized technique that only certain bee species have mastered. The bumblebee you're watching is using controlled vibration as a tool, essentially playing the flower like a musical instrument tuned to a frequency that causes it to release its pollen. It's acoustic engineering performed by an insect, using sound waves as a key to unlock resources that would otherwise remain inaccessible. You notice evening primrose buds near the edge of the meadow, and these plants are about to demonstrate one of nature's most dramatic transformations. Evening primroses are aptly named. Their flowers open rapidly at dusk, in some species taking less than a minute to unfold from tight bud to open bloom. This rapid opening is triggered by decreasing light levels and cooling temperatures. The flowers bloom at night because they're pollinated primarily by moths, which are active after dark. But here's the fascinating detail: you can actually watch evening primrose flowers open if you're patient and observant. The petals unfurl in visible real-time, like something from a time-lapse video, except it's happening right before your eyes at normal speed. The primrose buds near you are preparing for this transformation, waiting for the precise environmental cues that tell them night has arrived and their pollinators are beginning their rounds. In perhaps an hour, these closed buds will be fully open flowers, completing a transformation that most people never witness because they're not in the meadow at the exact right moment. Looking up at the evolving sky, you notice thin bands of pink and purple striating the high atmosphere above the sunset colors. These are called anticrepuscular rays. While crepuscular rays appear to radiate from the sun, anticrepuscular rays appear to converge toward the anti-solar point, the point in the sky directly opposite the sun. These rays are actually the continuation of the crepuscular rays you saw earlier, but because they're parallel and you're viewing them from the middle, perspective makes them appear to converge in the opposite direction. It's the same optical effect that makes parallel roads or railroad tracks appear to meet at a distant point. The rays above you are shadows of clouds or mountains cast across the entire dome of the sky, so long that they stretch from one horizon to the other, made visible by dust and moisture in the atmosphere scattering light differently in the shadowed and illuminated bands. You're seeing shadows that span half the visible sky, viewing the same light show from multiple angles simultaneously. A late-flying butterfly, perhaps a buckeye or a question mark, makes a final pass through the meadow before seeking its roosting spot for the night. Butterflies don't fly at night, and they must find safe places to spend the hours of darkness. They typically roost on the undersides of leaves, in dense grass, or among branches where they're protected from wind and somewhat concealed from predators. But here's something interesting: butterflies that roost together in groups have higher survival rates than those that roost alone, possibly because multiple individuals are more likely to detect approaching predators, or because the group provides some thermal benefits. Some species have traditional roosting sites that are used by multiple generations, though how this information is transmitted remains something of a mystery. Individual butterflies don't live long enough to teach their offspring, yet certain spots are used year after year. The butterfly passing by you is heading toward its chosen roosting spot, navigating by landmarks and fading light to a place where it will spend the next 12 hours in complete stillness, waiting for tomorrow's sun to warm its flight muscles and allow it to fly again. The light has grown soft and diffuse now, the direct rays of the sun replaced by the gentle glow of reflected light from the sky and clouds. The meadow has entered that magical time of blue hour approaching, when colors simultaneously deepen and soften, and everything takes on a dreamlike quality. The temperature has dropped noticeably, and you can feel the coolness rising from the ground, the earth releasing the heat it stored throughout the day. You realize that you've witnessed an entire day's cycle in this meadow, from bright afternoon through golden hour and now into the approach of evening. The meadow has shown you 100 different faces, revealed 100 secrets, demonstrated 100 ways that life adapts, survives, and thrives. You've learned to read clouds like books, to see flowers as engineering marvels, to understand that butterflies navigate using senses you don't possess through a world more colorful than you can imagine. The meadow has been your teacher, and the lesson has been patient, gentle, and profound. The sun has slipped below the horizon now, leaving behind a sky painted in gradients of color that seem to encompass every shade between deep blue and soft coral. This is the blue hour, that brief period of twilight when the world exists in a state of balance, not quite day, not quite night, but something precious and fleeting in between. The meadow has transformed once more, becoming a place of whispers and shadows, of cooling air and settling dew. You've been here for hours now, and you feel both energized and deeply peaceful, as if the meadow has recalibrated something essential within you. You notice that dew is beginning to form on the grass around your blanket, tiny droplets catching the remaining light like scattered diamonds. Dew formation is a fascinating process that demonstrates how water moves between states in response to temperature changes. As the ground radiates heat into the darkening sky and cools down, the air immediately above the ground also cools. Cool air holds less moisture than warm air, so when the air temperature drops to the dew point, the temperature at which air becomes saturated with water vapor, the excess moisture condenses into liquid droplets on cool surfaces like grass blades, leaves, and spider webs. But here's what makes this particularly interesting. Dew doesn't fall from the sky like rain, it forms directly on surfaces through condensation, pulled from the air itself. The droplets appearing on the grass around you are made of water that was invisible just moments ago, moisture that was part of the air you were breathing, now made visible and tangible by nothing more than the cooling of evening. The meadow is creating its own water from the atmosphere, harvesting moisture from the air through temperature alone. Above you, the first stars are beginning to appear in the deepening blue of the eastern sky, and soon the night shift of meadow creatures will fully awaken. The transition from day to night in a meadow is like a changing of the guard, with diurnal species settling in to rest while nocturnal species emerge to begin their activities. Moths, which have been roosting quietly throughout the day, will soon take flight to visit flowers that the butterflies have abandoned. And moths are extraordinary in their own right. Many moth species can detect the scent of flowers from over a mile away using their feathery antennae, which have far more surface area than butterfly antennae and can detect just a few molecules of scent. Some male moths can detect the pheromones of females from distances of several miles, following scent trails through the darkness with precision that seems almost supernatural. The quiet meadow around you will soon be full of moths navigating by scent and starlight, visiting the flowers that have waited all day for these nighttime pollinators. You notice fireflies beginning to appear, tiny sparks of cool yellow-green light floating through the gathering darkness. Fireflies produce light through a chemical reaction in their abdomen called bioluminescence, combining a substance called luciferin with oxygen in the presence of an enzyme called luciferase. This reaction produces light with almost no heat. It's one of the most efficient light sources known, with nearly 100% of the energy converted to light rather than heat. In contrast, a standard incandescent bulb converts only about 10% of its energy to light, wasting the rest as heat. But here's the truly remarkable part: each firefly species has its own unique flash pattern, different durations, different intervals, different rhythms. These flash patterns are essentially a language, with males flashing in species-specific sequences to attract females, and females responding with their own precisely timed flashes. The fireflies beginning to light up your meadow are engaging in a conversation composed entirely of light, with each flash a word in a luminous dialogue that has been perfected over millions of years. You're watching living Morse code, a messaging system written in bioluminescence. The western sky still glows with the last remnants of sunset, bands of orange fading to pink, fading to purple, fading finally to the deep blue of approaching night. This lingering light has a name: astronomical twilight. Even after the sun has dropped well below the horizon, sunlight continues to illuminate the upper atmosphere, scattered by air molecules and particles at high altitudes. Astronomical twilight lasts until the sun is 18 degrees below the horizon. Only then is the sky truly dark. The glow you're watching represents sunlight that's traveling hundreds of miles above Earth's surface, bouncing off the uppermost layers of atmosphere and finding its way to your eyes through a long, indirect path. You're seeing light that has traveled 93 million miles from the sun, then climbed high into Earth's atmosphere before descending to illuminate the evening meadow. The glow itself is the day refusing to fully surrender, light from a sun that set long ago still finding ways to reach you. You hear the first calls of nighthawks overhead, their distinctive peent sounds as they begin their aerial insect hunting. Nighthawks, despite their name, aren't hawks at all but members of the nightjar family, and they're perfectly adapted for catching flying insects in midair. Their mouths are enormous relative to their body size, surrounded by bristles that help funnel insects into their gaping maws as they fly. But here's something extraordinary: nighthawks migrate thousands of miles, with some traveling from Canada to Argentina and back each year, a round-trip journey of up to 16,000 miles. The nighthawks you hear calling above might be preparing for this epic journey, fattening up on the meadow's abundant flying insects before beginning a migration that will take them across entire continents. These birds experience more daylight than almost any other creature. By migrating between the far north and far south with the seasons, they live in an almost perpetual summer, following the long days and abundant insects across the hemisphere. Near your blanket, you can just make out the silhouette of a rabbit, its ears alert, testing the evening air with its nose. Rabbits are crepuscular, meaning they're most active during twilight hours, dawn and dusk, when there's just enough light to see but enough darkness to provide some cover from predators. But here's something remarkable about rabbit vision: their eyes are positioned on the sides of their head, giving them nearly 360-degree vision. They can see almost everything around them without turning their head, with only a small blind spot directly in front of their nose and directly behind their head. This panoramic vision comes with a trade-off. Rabbits have very little binocular vision and poor depth perception directly in front of them, which is why they often move their heads from side to side, using motion parallax to judge distances. The rabbit near you is monitoring the entire meadow simultaneously, its vision designed not for focusing on details but for detecting danger from any direction. It lives in a visual world fundamentally different from yours, seeing everything at once but nothing in great detail, perfectly adapted for a life where awareness of surroundings means the difference between life and death. The evening primrose buds you noticed earlier have begun to open, and if you watch carefully, you can actually see the transformation happening. The petals unfurl with visible motion, unfolding from their twisted bud formation into open, four-petaled flowers that seem to glow pale yellow in the failing light. This opening is driven by rapid cell growth on the inner surface of the petals, causing them to curve outward. The flowers will remain open through the night, offering nectar to moths and other nocturnal pollinators, and will wilt and close by tomorrow afternoon, each bloom lasting just one night and morning. The primroses are demonstrating one of nature's most elegant solutions to the challenge of pollination. Rather than competing with the thousands of day-blooming flowers for the attention of day-flying pollinators, they've specialized in serving the night shift, blooming when competition is minimal and their target pollinators are most active. You're witnessing a flower's entire adult life compressed into a few hours, from opening through pollination to closing, a complete story told in a single night. Above you, the sky has darkened enough that you can see the Milky Way beginning to appear, a faint band of light stretching across the heavens. This river of stars is actually our view of our own galaxy from inside it, looking through the disk of billions of stars that make up the Milky Way. But here's something that connects the meadow beneath you to the cosmos above. Every atom in your body and in every living thing in this meadow was forged in the heart of a star. The carbon in the grass, the nitrogen in the proteins of the butterflies, the calcium in the rabbit's bones, the oxygen you're breathing, all of it was created in nuclear fusion reactions deep within ancient stars that lived and died billions of years ago, scattering their enriched remains across space. The meadow around you, and you yourself, are made of stardust, literally composed of atoms that were once part of stars that no longer exist. The connection between the life around you and the stars appearing above isn't metaphorical, it's chemical, physical, and absolute. You and this meadow are the universe looking at itself, made of the same elements, governed by the same physics, part of the same unbroken chain of existence that stretches from the Big Bang to this quiet evening moment. As full darkness approaches, you hear a different sound, the high-pitched echolocation calls of bats beginning their nightly hunt for insects. Bats use echolocation with remarkable precision, emitting ultrasonic calls and listening for the echoes that bounce back from objects in their environment. Some bat species can detect objects as thin as a human hair and can distinguish between different types of insects based on the acoustic signature of their echoes. But here's what's truly extraordinary: bats aren't just passively listening, they're actively adjusting their calls in real time based on what they're detecting, changing the frequency, duration, and rhythm of their vocalizations as they close in on prey. It's called the feeding buzz, and when a bat is about to catch an insect, it increases its call rate to as many as 200 calls per second, creating an almost continuous stream of sonar information. The bats flying above you are essentially seeing with sound, building three-dimensional acoustic images of the meadow and everything in it, navigating and hunting through a sensory world that humans can barely imagine. They're experiencing this meadow in a completely different dimension, not as sights and shapes but as echoes and acoustic textures, a world made of reflected sound. You take a deep breath of the evening air, cool and fragrant with the mingled scents of grass, earth, and flowers. The meadow has grown quiet in a different way now. The daytime sounds of bees and birds have been replaced by the evening chorus of crickets and katydids, their rhythmic chirping creating a blanket of sound that seems to come from everywhere and nowhere at once. The last light has faded from the western sky, and the stars are appearing in greater numbers with each passing minute. You've spent an entire afternoon and evening in this meadow, and it has given you more than you knew to ask for. You realize that this meadow, which seemed at first like a simple place to rest, is actually a universe unto itself, a place where every flower is an engineering marvel, every butterfly a navigator using senses you don't possess, every cloud a sculpture of water and light constantly being created and destroyed, every blade of grass part of an underground network of cooperation and communication. You came here to rest, but you've discovered something more profound: connection. Connection to the rhythms of life that continue regardless of human observation, to the patient unfolding of evolutionary adaptations refined over millions of years, to the immediate present moment where dew forms and flowers open and stars appear and everything is exactly as it should be. The meadow has taught you its most important lesson, that wonder isn't something you have to travel far to find. It's everywhere, in every square foot of wild space, waiting patiently for anyone willing to sit still long enough to see it. The extraordinary is ordinary here, woven into every interaction between plant and pollinator, every transformation of water from liquid to vapor to cloud to dew, every navigation by magnetic field and starlight, every conversation conducted in flashes of bioluminescence. As you finally gather your blanket and prepare to leave, you carry with you not just memories but a new way of seeing. You understand now that you're never separate from nature, you're always inside it, made of it, part of the same fabric that connects fireflies to stars, roots to rain, and one moment to the next in an unbroken chain of being. The meadow will be here tomorrow, continuing its ancient rhythms, waiting for the next person willing to sit still long enough to hear its stories. And you, changed by this afternoon of lazy observation, will carry this meadow with you wherever you go, 100 facts that are really one truth: everything is connected, everything is remarkable, and wonder is always within reach for those who take the time to look.